Hi everyone, I'm Haochuan Guan from Tsinghua University. Today I'm very excited to talk about our work titled Core Sketch on exact computation of median absolute deviation with limited space. This presentation will be divided into four main sections: introduction, preliminary, MAD computation, and experiments. We'll start by introducing the background and purpose of this work in the introduction section. MAD is highly valuable in the context of big data era. It's derived from the medium of a dataset and serves the purpose of describing the extent to which elements within the dataset fluctuate around the medium. This is similar to the concepts of mean and standard deviation for a dataset. However, MAD demonstrates greater robustness in handling outliers, making it particularly effective in outlier detection. Notably, database systems such as InfluxDB and IoTDB have integrated MAD query functions to support outlier detection. Furthermore, we've recognized that calculating MAD, especially the exact MAD rather than the approximate one, is crucial. This necessity arises from the fact that approximate MAD might introduce significant deviations from the exact MAD values, consequently affecting downstream tasks such as the effectiveness of outlier detection. To illustrate this point, consider the following two datasets. We applied both exact and approximate MAD methods for outlier detection. It becomes evident that the outlier value threshold derived from the two methods deviate substantially. Our experiment substantiates that employing the approximate MAD for outlier detection could result in as low as 0.5 of the precision or recall score. However, obtaining the exact MAD presents challenges due to the following reasons. In the no-sketch approach, as depicted in the left diagram, for a dataset, we directly load all the data into memory and perform the necessary calculations. This method is accurate. However, in the context of big data size can often reach hundreds of gigabytes, exceeding the memory capacity of typical machines, rendering this approach impractical for real-world use. On the other hand, in the DD-sketch approach illustrated in the right diagram, the algorithm doesn't store all the data in memory while processing the dataset. Instead, it aggregates statistical information about the data in a data structure called a sketch. A sketch typically occupies only kilobyte or megabyte level sizes. Through two rounds of sketch construction, we can obtain an approximate median of the dataset and an approximate MAD of the dataset. Although this method is feasible on the limited space, it is not an exact approach. As a result, the intuition is whether we can combine the strengths of both techniques, leveraging the accuracy of no-sketch approach and the space efficiency of DD-sketch approach. Based on this insight, we introduce a data structure called Core Sketch for calculating the exact MAD as illustrated in the diagram on the right. During the data preprocessing phase, Core Sketch in the diagram stores statistical information about the dataset in memory. It utilizes sketch refinement techniques to progressively narrow down the range of the median and MAD, ultimately performing calculations using a minimal amount of data. This approach aims to achieve exact MAD computation even on the limited space. Thus, our contributions are outlined as follows. We devised a sketch structure called Core Sketch, and we presented the algorithm of computing exact MAD using Core Sketch. We then proved the mergeability of Core Sketch and the convergence of the iterative algorithm based on Core Sketch. The time and space complexity of the algorithm is also computed. We have also conducted extensive experiments over real and synthetic data sets. Before delving into the MAD computation process, let's first introduce some preliminary concepts. First, we present the problem statement. The definition of MAD is the median of the absolute differences between the elements and the median of the dataset. In this diagram, we provide an example to illustrate what MAD represents. For a dataset on the number line, containing 7 elements in total, the fourth largest element, which is 5, serves as the median. And the value, which is the fourth furthest from 5, and that is 3, becomes the MAD element, which is eta in the formula. Consequently, we obtain a MAD of 2. It is 3 minus 5 and take the absolute value. Now focusing on Core Sketch, its targeted problem is exact MAD computation with limited space. That is, with a limited number of buckets in the sketch, the problem is to compute the exact MAD of a given dataset D. From this foundation, we can devise the following sketch structure. Firstly, we introduce a novel concept termed the bucket boundary domain. It constitutes a set defined as follows, where the elements exhibit an exponential relationship among them. Core sketch is then constructed as depicted in the following diagram, comprising a sequence of buckets with the boundaries of each bucket falling within the bucket boundary domain. Within each bucket, the count of elements falling within a specific range is recorded. Notably, the utilization of bucket boundary domain yields two significant advantages. The first lies in easing parallel computation and guaranteeing mergeability, while the second advantage pertains to supporting refinement of the sketch. Building upon the previously described sketch structure, let's now delve into the process of MAD computation. The diagram depicts the iterative algorithm process for computing the exact median absolute deviation using core sketch technique. As shown, we started by reading data from the disk, which serves as the input of the algorithm. Subsequently, based on the dataset, we construct a sketch. Using this sketch, we initially compute buckets for the median and MAD bounds as illustrated in the diagram. These buckets are represented by the red and blue segments on the axis below. Following this, we utilize these buckets to determine the ranges of the median and MAD elements. Moving forward, we delve into the iterative phase. Firstly, we refine the sketch based on the ranges of the median and MAD elements. Afterwards, we recompute the buckets and ranges on the refined sketch. This process continues iteratively until the elements within these three segments of ranges can be accommodated in memory. At this point, the exact MAD can be calculated using a no-sketch method. Firstly, I will present the steps for sketch construction. During the process of creating a sketch, it needs to adhere to two conditions. Firstly, the sketch must cover the entire range of dataset. Secondly, the buckets within the sketch should be as finely partitioned as possible while staying within the constraint of limited space. The diagram on the right provides an example of sketch construction. In the uppermost sketch representation, that is the first axis, the buckets are not finely partitioned enough, and in the lowest sketch representation, and that is the third line, the number of buckets exceeds the capacity of the limited space, that is M. So the second sketch illustration represents the desired sketch that fulfills these requirements. That is, it covers the range of data and can be as fine as possible while the bucket number doesn't exceed M. Based on the constructed sketch, our initial step involves calculating buckets that will be utilized to bound the median absolute deviation and median values. We are primarily seeking two types of buckets, and the first type is the median bucket, denoted as BM, which corresponds to a specific bucket in the core sketch that bounds the median value. The second type comprises MAD buckets, denoted as BL and BR, which correspond to two distinct buckets within the core sketch. These MAD buckets and median bucket are employed to establish boundaries that encompass the MAD value. And the figure provides an example of identifying median and MAD buckets within the sketch. The specific mechanism for this identification is explained in detail in the paper. The ranges of median and MAD elements are determined by the left and right boundaries of the median bucket and the MAD buckets. Here, we are using only two buckets as an example. In practical implementation, it is essential to utilize three buckets simultaneously for calculating of the ranges instead of the two in this picture. As evident, by utilizing the median buckets, we can directly derive the range of the median. Subsequently, with the aid of both the median bucket and the MAD buckets, we can compute the upper and lower bounds of the median absolute deviation, denoted as dmin and dmax, thereby obtaining the ranges of MAD elements etc. Next, we delve into the iterative phase of the algorithm. Since we've already obtained the ranges of the median and MAD elements, and the calculation of MAD essentially involves computing the median and MAD elements, we simply need to continue constructing sketches within these ranges that is the range of MAD elements, and median to narrow down the values of the median MAD elements. This process allows us to approach the exact MAD. The refinement of these sketches essentially involves creating new finite sketches within the established ranges. This process is akin to the initial sketch construction process, as shown in this figure. Following that, similar to the previous mentioned process of identifying buckets for median and MAD bounds, we can obtain median and MAD buckets in this refined sketch. It's important to take into account that in this step, we need to include the elements between the ranges that were not covered by the sketch, that is in I1, I2. Similarly to before, we can calculate new ranges for median and MAD element using the median and MAD buckets. However, it's worth noting that the median and MAD element belong to both the new ranges computed, shown as red in this figure, and the previous ranges shown as blue in these figures. Therefore, we take the intersection of these ranges and take it as the new range for median and MAD elements. When the sketch is sufficiently refined, meaning that the data elements within the ranges of the median and the MAD elements can fit into memory, we proceed to load the elements within these ranges into memory. We then employ the no-sketch method to perform the calculation of the exact MAD. The diagram illustrates how to utilize the elements within the ranges of median and MAD elements to locate the median and MAD element in the original data set. We can see that we just accumulate all the data ranks before lambda or before eta to do this. And now we present our evaluation of the proposed algorithm. We use 3 real-world datasets and 3 synthetic datasets. They are normal, chi-square, Pareto, Bitcoin, gas, and power. And there are several baseline algorithms in total. Firstly, there's the precise or exact no-sketch algorithm, quick select. And DD-sketch and TP-MAD are both approximate MAD computation methods, which are just proposed in the latest years. Regarding our proposed core sketch, we evaluated it into 2 modes, single-threaded and 4-threaded. And 4 metrics are considered, including query time cost, memory space cost, relative error, and F1 score of outlier detection. Due to the limited time, the result of relative error and F1 score will not be presented, but can be found in the paper. Regarding the dataset size, we observed that core sketch still exhibits competitive performance in terms of time. Additionally, it is evident that due to the dataset size significantly exceeding memory capacity, no-sketch is unable to return results when the data volume reaches 10 billion. As for the approximate methods, the results returned under constrained space might exhibit relatively significant relative errors. By alternating the bucket limit, which refers to the maximum number of buckets in the sketch as shown in the diagram, we can observe that with a smaller bucket limit, the approximate methods return results with large relative errors. This highlights the superiority of core sketch in limited space scenarios. We also implement our method in database systems, including Apache IoTDB. It can be observed that core sketch can support up to 32 concurrent queries, whereas the no-sketch method, due to its significant memory consumption, can support a maximum of only 4 concurrent queries. So to conclude, in this paper, based on the pros and cons of no-sketch and DD-sketch algorithm, we propose core sketch to support exact MAD computation under limited space. The refinement scheme of sketch gradually narrows down the ranges of the median and MAD elements, and once the ranges of data elements are small enough to be stored in memory, the exact MAD is computed. The mergeability of core sketch, the convergence of the iterative algorithm based on core sketch, and the time and space complexity are all given in the paper. Evaluation over synthetic and real-world data sets with 4 metrics are also given in this paper. We deploy our core sketch algorithm in Apache IoTDB for database system use. It is served as a query function in IoTDB. And that's all. Thanks for your listening.